Welcome everybody to another lesson on logic. In today's lesson, we are going to look at propositions and truth tables. Truth tables are basically the way that we're going to figure out whether or not these propositions are true and false. So a proposition is just a claim. It's some sort of assertion or denial. It's basically you're saying that here is something and it can either be true or false. And usually propositions are written in the structure of a complete sentence. And it has to be something that, can be either true or false. So that's a big thing. You got to make sure that when you're coming up with these propositions, they're binary things, right? They can only have two options. Either they are true or they are false. And then a truth table is just a way of designating the values of different propositions and then figuring out what happens if you have an or an and or an if and all these different things that we're going to do with propositions. So it's a way of kind of keeping your truths and false, T's and F's organized. So here's a simple example. The negation of a proposition is just, we say not P, and we normally use this little symbol here, the little squiggly, I think it's called a tilde. And it's in the upper left-hand corner of most keyboards. And so if P is true, then obviously not P would be false. And if this proposition P, remember P can just be any statement, like my hair is black. Well, okay, it's true. And then not P would be my hair is not black. And so if it was true, then it was false, right? If P is my hair is pink, well, then that would be a false statement for me personally. And then this would be my hair is not pink, which would of course be true. Right, so that's the idea of it should be a fairly, don't overthink it. Obviously, P and not P are opposites, and they're normally written as just that. It's like the not P statement is usually just the exact same statement as P with a not in there somewhere. So find the negation of the proposition, Amanda is the fastest runner on the team. Okay, so write its negation. Now here's where it gets tricky. You think, okay, Amanda is the fastest runner on the team, so the negation would be Amanda is the slowest runner on the team, but that's not true. You don't want to negate the verb or the adjective, right? You don't want to go from fastest to slowest. Really, the true negation is to just take the original thing and put a not in there. So the negation of that proposition is simply Amanda is not the fastest runner on the team. Because if she was the second fastest, that would still not be the fastest, right? And if she was the third fastest, that would still not be the fastest. So to go all the way to the extreme of saying she's the slowest, being the fastest and being the slowest, those aren't opposites. They're not what we call complements. They don't, if you put them together, they don't take into account all the possibilities. Okay, so it's kind of like saying, if you rolled a six-sided die and you rolled a six, well, the negation of that isn't rolling a five, it's just rolling anything but a six, right? So keep that in mind. It has to, those two things, when you put a negation with a regular proposition, those two statements put together have to basically encapsulate all possibilities for that particular, statement-y scenario thing. Okay, so the double negation, not, just gets you back to the original. So if your proposition P is true, then of course not P is false, but then not P becomes true. So, in English, it's stupid. You wouldn't say that, my hair is not black, or my hair is not pink. It's a double negative. It's silly. But we have to think about these things in terms of logic. It's the idea that, think of it as positive and negative numbers, right? If you have a positive number and then you negate it, it becomes a negative, right? So you go from 3 to -3. And then if you take the negative of -3, it becomes +3 again, right? It's like two negatives get you back to a positive. It's the same kind of idea with these double negations, right? So that we even have a negative negation. So here's an example. After reviewing data showing an association between low-level radiation and cancer among older workers at the Oak Ridge National Laboratory, a health scientist from the University of North Carolina at Chapel Hill was asked about the possibility of a similar association among young workers at another national laboratory. He was quoted as saying in the Boulder Daily Camera, "My opinion is that it's unlikely that there is no association." You see how that's a double negative? Does a scientist think there is an association between level radiation and cancer among young patients? Well, he isn't coming out, or well, I guess it's a he was quoted. He isn't coming out and saying that there is an association. He's just saying it's unlikely there is no association. So you see how there's a difference. That he didn't really say, oh yeah, there's an association. He's just saying, I don't think that there is no association, right? It's kind of a wishy-washy statement, but that's an example of a double negation. So because the words unlikely and no association, you can think that the scientist's statement contains a double negation. And so P being our statement is it's likely that there is an association between low-level radiation and cancer. The word unlikely gives us the statement it's unlikely that there is an association, which we would identify as not P. And then the words no association transform the statement into the original statement. It's unlikely that there's no association, which we recognize as not P. Right? So you can see that if we set this up as just the standard equation, then if we put unlikely and no association, we get two negatives, and we get back to this whole thing of saying it's likely that there is an association, which we can all kind of read between the lines and see that that's what the scientist was saying. They were just trying to say it in a wishy-washy way, but logically they are equivalent statements. Okay, so because the double negation has the same truth value as the original proposition, we conclude that the scientist believes that there likely is an association between low-level radiation and cancer. Now, that's a dangerous thing to assume. You know, we're kind of putting words in people's mouths, but logically speaking, that's what the scientist was saying. Okay, so propositions are often joined with what are called logical connectors, things like and, or, and if then. So a simple example is P is going to be the proposition I won the game, and Q is going to be the proposition it was fun. So if we use the logical connector and, it would be I won the game and it was fun. That's a simple P and Q. We could say I won the game or it was fun, and that's a P or Q. And then we could say if I won the game, then it was fun, and that is if P, then Q. And order does matter as far as, which comes first. If P then Q is different than if Q then P. With and or, order doesn't matter. Because P and Q is the same thing as Q and P, and P or Q is the same thing as Q or P. It's only if then. And think about if then is like an arrow with a direction. You draw an arrow from the first thing to the second thing. So that's why order matters with if then, because then the direction of the arrow would change. So here is the symbol. It's kind of like a little upside down V that we normally use for and. And the rules are that P and Q is only true when they are both true. So an and, which what we call a conjunction, is a very picky thing. But think about it this way. Let's say you were young and you were back living with your parents, and they put stipulations on whether or not you get an allowance. And they're only going to pay you an allowance if you both clean up your room and take out the trash, right? So P could be cleaning up the room. Q could be taking out the trash. So if you clean the room and take out the trash, then you get your allowance. But if you clean your room but you don't take out the trash, they ain't going to pay you anything, right? If you don't clean your room but you take out the trash, still no allowance. And if you don't do either, then of course you're not going to get your allowance. So that's kind of the way to think about an and, is you have to do both to get paid, so to speak. So you have to do both. They both have to be true in order for the whole thing to be truth. Okay, well, let's say your parents well, here's an example. The capital of France is Paris, and Antarctica is cold. The capital of France is Paris, and the capital of America is Madrid, right? So the statement contains two distinct propositions. The capital of France is Paris and Antarctica is cold. Because both propositions are true, their conjunction is true. But obviously with the second one, even though the capital of Paris is true, the capital of America is not Madrid, so therefore that one is false. So let's say your parents are a little more lenient. And instead of you have to do both to get your allowance, they say to get your allowance, you just have to take out the trash or clean your room. Well, there are two types of or. There's what's called the inclusive or, where you can do either or both and it's still good. Or there's the exclusive or, which means you can do one or the other but not both. When we're dealing with logic, we always assume we are using the inclusive or unless we're told otherwise. And this will make a little bit more sense when we look at the truth table. So again, P is cleaning your room, Q is taking out the trash, and your parents said you're going to get your allowance if you just do either of them. So in this case, you did both, which is awesome, and you get your allowance. In this case, you cleaned your room, but you didn't take out the trash, so you still get your allowance. Here, you didn't clean your room, but you did take out the trash, so you still get your allowance. And here, again, you were lazy and didn't do either, so you didn't get your allowance. So you can see that the or is a much more lenient rule, right? With the and, it's only true when you do both. With the or, it's only false when you don't do both, right? That's what it means for the inclusive, because here is where it's just one or the other, and then here's where it's both. So if it was an exclusive or, this would be false. But in logic, we let that be true, okay? So if either or both is true, then the whole thing is true. And then instead of the upside down V, we use the V symbol for or. If you've ever looked at unions and in set theory, you see it's a U, and then intersections are like an upside down U. It's kind of those same similar symbols. So here's an example. Consider the statement, airplanes can fly or cows can read. Is this a true statement? Well, of course it's a true statement because airplanes can fly, even though cows can read is false. So that's the idea of it only has to be one or the other. I don't know, maybe you found a cow that can read. Okay, if-then statements, which are sometimes called conditionals or implications. It's basically saying something implies something else. So we've got P and Q, and then we've got to set up all the different ways this can happen, right? They can both be true. We can have a true false. We can have a false true. We can have a false false. And this is if P then Q. So this is saying if P is true, then Q is true. That's a true statement. If P is true and then Q is false, that's a false statement. And then if P is false but Q is true, that's true, and false false is also true. So the way I like to think about these, the way I've always kind of taught it to my students, is it's kind of like you're saying, if you do something, then I'll do something in return. So like, if you come to my party, then I'll give you a parting gift, right? So I'm making that claim. If you show up to my party, I'm going to give you a gift. So if you show up to my party and I give you the gift that I promised you, then I was true to my word. If you show up to my party and I don't give you that gift, then I lied, and that was a false statement. But if you don't even show up to my party, then my statement is true by default, because I said, if you show up to my party, I'm going to give you this gift. Well, if you don't show up to the party, but I still somehow later on give you a gift, well, that was a true statement. But also, if you don't show up to my party and I don't give you a gift, that was still a true statement, because I'm under no obligation to give you the gift because you didn't show up. So that's kind of the weird thing with if-thens, is an if-then is always true, except for the one case where basically P holds up their end of the bargain and Q fails to do so, then it's a false statement. So if the first part is true and the second part is false, then the whole thing falls apart. Otherwise, it's always considered true. Okay, so there's some alternate phrasings of conditionals. And it's just ways to kind of help you understand why they're true and false when they're true and false. So they're saying P is sufficient for Q, P will lead to Q, P implies Q, P is necessary, or sorry, Q is necessary for P, Q if P, and Q whenever P. So you can see how P leads to Q. And so when P doesn't happen, it really doesn't matter what happens with Q. That's how we get the whole true and false things. So some variations on the conditional. And these are just ways of kind of restating the conditionals, right? So with the original conditional, if P then Q, so we've got if it is raining, then I will bring an umbrella to work, all right? So that's just your standard if P then Q. The converse is if Q then P. So we're going to have converse, inverse, and contrapositive. And I know, I'm sorry guys, it's a lot of crappy vocabulary, but the converse is basically just going in the opposite direction. So if Q, then P. So if I bring an umbrella to work, then it must be raining, right? That's the if Q, then P. The inverse is same direction, right? So we still go from P to Q, but everything is inverted. Everything is negated. So if not P, then not Q. So if it is not raining, then I will not bring an umbrella to work. And then the contrapositive, you can think of as it's the most convoluted thing where both things are flipped. We flip the direction and we negate everything, right? So the converse just flips the direction. The inverse, right, negates things. It inverts the, I don't know how you want to think about it, inverts it so that it's negative, and then the contrapositive does both. So you can see it goes from Q to P, but they're now both not. So if not Q, then not P. If I do not bring an umbrella to work, then it must not be raining. So those are those three things: converse, inverse, and contrapositive. And we can also use symbols for those as well. Usually, like I said, if P then Q, we can just draw P with an arrow to Q. And then the knots would be, little squiggly things. So here we start off with our regular table of P's and Q's, right? True, 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 false, false, true, false, false. And then we put in the opposites, the not P and the not Q. So they're obviously just the opposites, right? False, 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 true, true, false, and true, true. So then we can figure out how all of these things work out for trues and false. So if P, then Q. So true to true, right, is true. If true, then false. Remember, that's our only false. You came to my party and I didn't give you anything. And then the last two, we call them, like, I can't remember the phrase, but they're true by default, right? Because P didn't happen, so they're true no matter what. So if Q, then P, we're just going in the opposite direction. So if you do this, then this happens to happen. Also true. So you didn't do anything, so it doesn't matter. True, right? You did what you're supposed to, but they didn't follow through, so there's your false. And then again, you didn't do anything, so it doesn't matter, so there's your true. Okay, now they say these two things are logically equivalent. This is in the wrong place, right? These two things are not logically equivalent. So let me move this so you don't get confused. These two things are logically equivalent. Can you see that? Because the trues and falses are all in the same spot. So the converse and the inverse, even though they do, different things, they are logically equivalent. So if Q, then P is the same thing as if not P, then not Q. And then you can see that these two things are logically equivalent. So the idea is if you change the direction and you negate things, it's that whole double negative thing. And that double negative gets you back to where you started, right? So if not P, then not Q, the inverse is going to get you the same logical statements as just the converse. And then the contrapositive, where you negate everything and you change the direction, gets you right back to the original statement. All right, just a couple more. Here's an example. Consider the true statement. If a creature is a whale, then it is a mammal. Write its converse, inverse, contrapositive, evaluate the truth of each, and so on and so forth. So the statement has the form of if P then Q, where P is a creature is a whale and Q is a creature is a mammal. Therefore, we can find the converse, if Q then P. If a creature is a mammal, then it is a whale. This statement is false because most mammals are not whales, right? The inverse, if not P, then not Q. If a creature is not a whale, then it is not a mammal. This statement is also false because there are plenty of things that aren't whales that are mammals, right? And then the contrapositive says, if not Q, then not P. And remember, so now we got to do the negation of the second part. So if a creature is not a mammal, then it is not a whale. And like the original statement, this is true because whales are mammals. And if you're not a whale, right? Or sorry, if you're not a mammal, you can't be a whale. So that's the idea of when you negate both things, you get back to the original value of it being true or it being false. Okay, so logical equivalence just tells us that the original proposition and its contrapositive will always have the same truth value and are logically equivalent. And then similarly, the converse and the inverse will always have the same truth value and are logically equivalent. If you remember, both the converse and the inverse were false statements, whereas both the original and the contrapositive were true statements. And that's it, guys. That's truth tables. I hope this helps.